This is a talk that I was poised to give to none other than the Defense Advanced Research Projects Agency. And my fun fact to start the presentation is that they found out I'm not a US citizen, that I'm a non-resident alien, and I was not allowed to speak to individuals with a clearance above SCI or whatever the fuck. Like above secret. So I was literally not allowed to contact these people on account of potentially poisoning their brains with commie gobbledygook or whatever the hell. I don't know. Knowledge. So anyway, yeah, the talk, okay, so we're talking about Chinese radios. They were scared that I was going to expose them to Chinese trade secrets or whatever the hell. That's what it was, now that I think about it. Must have been. Anyway, hello, my name is Andre, my call sign is K8TUN. I am a computer science and engineering, and electrical engineering graduate now at Case Western Reserve University, student at the time, am Townie LOL, my name is Tunas on Town. I've been an amateur radio operator since 2017 in Macedonia. I've been an amateur radio operator in the US since 2021. I am a massive CTF enthusiast and I love reverse engineering stuff. And I love messing with electronics. And we're going to talk about what the UV-K5 is, which is this mysterious thing that you have no idea about. Turns out that it is a cheap Chinese radio, and it costs less than $20 now. It has sold millions and millions of units on account of the work of the open source community. Inside it, it has a microcontroller, 16 whole kilobytes of RAM, and 64 whole kilobytes of flash memory. And it has several different variants. The one pictured is the UV-K5. There's also the UV-K6, UV-5R+. All of these are slightly different, but the general internals are the same. Same black and white screen, or monochrome. You know, I say black and white, it's actually blue on one of them for some reason. It contains this radio chip called the Beacon BK4819 chip. A fun fact about Beacon is that in Chinese, their name sort of translates to Broadcom. So in China, they're called Broadcom for some reason, which causes a lot of confusion when you're translating Chinese documents from Beacon and it says Broadcom Technologies. Apparently, intellectual property laws do not exist or are much weaker there. So it suffers from the same flaws as other CCRs, which is a category, an affectionate name for cheap Chinese radios, in that if it receives a strong signal on one frequency, it oversaturates the receiver's front end all across the board. So if someone transmits a strong signal at 200 megahertz, you can't really hear weaker signals on 100. The filtering is not very good. There is low dynamic range, which means, again, if there is a high at some point in the band, even if you're listening to a low somewhere else, it'll get drowned out by noise. But that's okay. It's $20. It is practically disposable. It does have advantages, though, in that its stock software is much better than other cheap Chinese handhelds, which are usually limited to like 99 channels, and you have a button to switch between whether you want to key in the frequency or you want to just do the channels, and maybe there's a setting to change the backlight to turn off at 10 seconds instead of 5, and that's it. It comes with some unique features, including air copy, which uses a frequency shift keying modem in the actual radio chip to talk from one radio to another and transparently copy all of the settings from one radio to another, effectively cloning all the channels, programming, settings, call signs, scan lists, anything that you would have on the little 8 kilobyte EEPROM in the radio. All 8 kilobytes get sent over the air at about 1200 bits per second, which uses a unique part of the radio chip that we use for other things, TBD later. It has a scrambler, which all it does is it takes the frequency range of your voice and it makes 2100 hertz, 1100 hertz, and it makes 1100 hertz, 2100 hertz. So it like literally inverts your voice, which is only as much of a scrambler in that you sound like you're going, and it's still very easy to pick out what you're saying. And also every single SDR software in existence has a plugin to descramble. So it has a frequency detector in that it actually tells you the strongest frequency around you, so you can just sit next to a security guard as they transmit and find out where they're transmitting, especially if it's analog. It has support for listening to AM, or amplitude modulation, which is notable because it is used by airplanes and air traffic control. Thankfully, it does not allow you to transmit in the same areas as air traffic control, as that would be catastrophic. We will touch upon this later. And also single sideband used in high-frequency communications, which are called high-frequency, but are actually at the lowest end of what we do today, which is 3 to 30 megahertz. And most importantly, the firmware can be upgraded using some Quansheng utilities. They provide a .bin file with the stock firmware, which, of course, the first thing we did was to see if it was encrypted at all, and it was. We'll get back to the encryption later, but there is a radio chip in there. I talked about it. It has a receive range of 18 to 1300 megahertz, which is absolutely bonkers for a thing that you can find in a $20 radio. The most obscure way that we found that chip was a toy walkie-talkie for children that was shaped like a little kit, like a cat, had little ears and stuff. The ears were the antenna. And it does 18 to 1300 megahertz and like FSK and stuff. So to us, it's a black box. And even to this day, we still don't know much about it. This is, as of 2023, in 2025, we do not know any more about it than we did before. We got some leaked documentation on the registers, and by leaked, I mean someone bought an evaluation board, someone who lived in China, and then machine translated all the documentation that came on a USB drive with it. And we found some stuff with trial and error. We're still working on figuring out the rest of it. So first reverse engineering attempts were in March 2023. I'm going to skip the history, but pretty much we sniffed the serial port data that was going between the computer and the radio when programming it and when flashing firmware, figured out that it was actually XORed. It appears encrypted. The actual file itself, the .bin file, appears encrypted, and the packet format is, is there a cursor? Yes, okay, cool. I'm just going to use the cursor to point. I thought it was invisible. It goes A, B, C, D, then the length of the packet, then absolute gibberish, and then DC, BA. And I was like, okay, cool. And we figured out that the updater was just a normal .NET application. I don't know if you can see, but all of the variable names are literally hieroglyphs. And when I say hieroglyphs, I mean actual Egyptian Unicode point hieroglyphs with a capital H. And there is a utility called D for dot that makes quick work of it and actually gives them the names that they're supposed to, because apparently their real names are somewhere and it just fishes them out of thin air. And we discovered the XOR key that was used to encrypt the communications between the radio and the computer over the serial port, 16-byte key, and we tried to decrypt the firmware with the same key, but it turns out that it's encrypted with a separate 128-bit XOR key, still 16 bytes. Thankfully, that was also stored in the updater, since the updater decrypts one XOR and encrypts it with another one. If it had just used the same 16-byte repeating key in the updater to send the data and have the radio be the one that does the decrypting on its side with that second key, and that second key did not leave the radio, it would have made our job significantly harder. But both of them were stored in the updater because it decrypts it before flashing to check if it's a version that it's suitable to flash. And if it's all XORed before it sends it to the radio, it has no way to actually check it. And now that we have figured out the communication and we figured out the encryption of the actual file, we're able to write arbitrary images to the device. And more importantly, we can also read the firmware image that goes onto the device. We put it into Ghidra. This is an early screenshot of Ghidra where we started writing stuff. And you can see we were not very sure about what stuff does, set up AGC, something with CDCSS, because there was a string that said CDCSS. And a note that's not in the presentation, but I will say, the stuff they had on the website, the initial firmware version still had some debug strings in them, which on a 64 kilobyte firmware is actually quite brave, because strings are big. They are, especially Chinese debug strings, they are multi-byte. They're like GB, whatever the code point was, I don't remember. But yeah, not a complete disassembly by any standard, and then we had a hero come in later on. But our initial attempts were to build what's pretty much like a ROM kitchen was in Android. It's a Python script that takes the firmware, patches some bytes that we discovered in Ghidra, shuffles them around, and unlocks the full reception range, changes the screen timeout length from 1 minute maximum to like 60 minutes maximum. and inverts the screen, because apparently when we debugged the LCD specification document, we found this command that would just invert, black becomes white, white becomes black. And so we found the offsets of this and literally patched the offsets in a very crude way. And then we made a little web flasher that would just emulate what the Quansheng original utility did. Bob's your uncle. Everyone had fun. And then we just re-encode it so that the official flasher could use it. And this is the web flasher called UV-Mod, and it was literally just, the most convenient application ever. It was a one-stop shop. You checked what you wanted your firmware to do. But we also figured out that we could take over the function, the interrupt, called the system tick handler, that runs every tick. So the tick is 72 megahertz divided by 1,000. It was about every 72 microseconds or something. I don't remember. But 1 over 72. But yeah, so in the end, we had a function that could run every so often. And what we did was we took over that function, took over the execution of the native operating system, and ran our own code once every tick before running the original system tick handler, and thus being able to do stuff like, I keep forgetting to use a pointer to just point at it. So this is the normal UI. It has channel A and channel B, but we also added an RSSI display, and we added this little graph of the RSSI display over time, because we ran the function once every so often, and all I had to do was just shift the previous values. And one of the things when we saw that we had an RSSI reading, and we had the ability to display RSSI over time, and if we vary the frequency over time, we get a spectrum analyzer, which I do not have pictured, but just imagine drawing bars on the screen with signal strength across a range, and you have yourself a spectrum analyzer from like 18 to 1300 megahertz. And finally, the state of the art, even to like 2025, is that someone took the entirety of the firmware and turned it into readable normal C, bit by bit, function by function, overlay by overlay, document by document, assembler instruction by assembler instruction, and called it Open Edition. And this allowed us to use the entirety of the space in the flash because we could recompile it with GCC 12 and not ARM-Keil 6 or MDK6 or whatever the hell it was. And the first time we compiled the source as is, it was already 30% smaller than the firmware image, which means that we freed up a lot of space for a lot of features. And this is some of the stuff that people have done with it. Top left corner is said spectrum analyzer, and you can tell it's already looking a lot cleaner. Someone soldered in a shortwave receive chip to actually be properly able to receive 14 megahertz and other high frequency transmissions. And then someone else made an FSK modem SMS, like text messenger. So it just sends messages from the radios, sends messages between the radios instead of just data. And it worked really fast. And then someone actually made a protocol out of it to like send RSSI and send have a packet that's like, who's there, and then collect responses. People's minds went absolutely crazy. Like it spawned a whole renaissance in custom firmware for this $120 radio. And as a retrospect, all of this stuff since 2023, we've done further hacking. We've done remote control using a PC, and that we now have like a .NET application that functions as a dock. And we did interface with a more powerful computer for digital communications because you could just use the headphone and microphone jack and then use powerful decoding software for FT8 and other stuff on a computer. And that concludes my talk. Hopefully it was, 5:52. Yeah. Thank you very much for your attention. That's the end of my talk.